UAV. So a quick overview of what we're going to be going over today. We'll go over our mission review, UAS design analysis, manufacturing plan and glider test, testing plans for next semester, and the updated budget and schedule for next semester, and any questions you guys have. So a quick review, a quick reminder of our mission. Our UAV will be doing a search and rescue to locate missing hikers in the Appalachian Trail using an RF sniffer, which will detect and pinpoint the location of the missing person based on their cell phone signal. Then we'll send the GPS coordinates to ground control for quick help deployment. So a quick overview for our top level requirements. Our UAV shall be hand launched. That's based on the Boeing constraints. It shall always communicate with the ground control, and it shall fly autonomously since it will be out of the line of sight. It shall also stay in the air for at least 90 minutes to provide a sufficient search duration, and it shall fly for at least 60 kilometers to the length of the Appalachian Trail, and it also shall have a safety switch, the kill switch in cases of an emergency. And now I'll turn this presentation to my teammate Quentin, who will go over the payload.
Looking at our UAV's payload, the largest component is the RF signal detector, which will be simulated in our case for cost reasons. The satellite communicator, also used to share lost hiker positions, will also be simulated for the same reason. Our onboard computer will be a Raspberry Pi, and our GPS sensor will be a micro MAN module. None of the components have changed since the PDR because of our propulsion system, aside from the propeller size. Evaluating it, we chose a folding propeller to reduce the possibility of propeller strike during our belly landing. The 1150-watt motor, which was chosen, provides about 15% more power than was absolutely necessary, which serves to make our takeoffs a bit easier. And our two 6-cell 5,000 milliamp batteries allow us to achieve our desired flight time of 90 minutes. Our decided upon 8-cell propeller allows us to achieve a new top speed of 21.5 meters per second, or roughly 48 miles per hour. This is important in case our UAV penetrates strong winds, which are highly likely in the Appalachians. Our vehicle will be able to cruise at about 50% throttle, gaining a speed of 11.6 meters per second, or about 26 miles per hour. Our energy analysis has been divided into 3 categories, including propulsion system during takeoff, propulsion system during cruise, and the avionics system throughout, as its power consumption won't vary significantly between flight phases. As you can see, our propulsion system during cruise demands the vast majority of the power, which makes sense as it represents all but roughly the 10-second full throttle blast used during our takeoff. And note that the roughly 6% extra refers to percentage of battery remaining after our 90 minutes of flight time. Initially, we were going to use a Pixhawk 2.1 for our flight control system. We were having trouble sourcing the correct compatible components, so we chose to do a Pixhawk 1 kit as it simplifies our component and purchasing. We selected RGPilot as our firmware because of our team's experience with it, and we selected Mission Planner as our ground control station in order to monitor our UAV status and mission from the ground. Here we have the component layout of our UAV. Our payload layout will be looked at in more detail in the next slide, but here you can see the mounting of the pivot tube on the left wing, which serves the purpose of providing more accurate velocity measurements to the Pixhawk in order to prevent an accidental stall. Additionally, you can see the mounting of the GPS and compass unit on top of the boom in order to prevent any signal obstruction and hindrance for optimal accuracy. A closer look at our payload layout. You can see that the batteries are placed up front, which is primarily to achieve our proper center of gravity. Internal shelving within the fuselage will be used to keep the various components in place and prevent shifts in weight distribution. And the I2C splitter will be placed on the left side of the fuselage so that it will be closer to the pivot tube, as this airspeed sensor will be connected to the I2C unit. Here's our wiring diagram, which shows how the various electronics in our UAV are going to be connected. The battery will be routed to a power module to provide battery information to the autopilot system, as well as connect to our electronic speed controller. Speed control will be connected to both the throttle input on the PIC-SOC as well as the motor unit. And the PIC-SOC has a number of connections shown that include GPS, airspeed sensor, telemetry, and more. Here's a connection diagram between each of our payload components. A USB connection will send data from the RF detector to the Raspberry Pi, where the Raspberry Pi can process the data and ping if it detects a cell phone signal. The Raspberry Pi will receive GPS data from the PIC-SOC via a 4-pin connection. It also sends commands to the PIC-SOC if necessary to control the UAV. And the Raspberry Pi will connect to a satellite communicator device via a Wi-Fi link. And this connection sends cell phone detection pings and GPS data to our ground station, from which commands can be sent back to the Raspberry Pi. Here's our aerodynamic drag analysis for our UAV. The table on the right shows the parameters at which our VSP aero drag analysis was tested, and the pie chart demonstrates the distribution of drag caused by the various components of the UAV. As you can see, the wing causes roughly 60% of the drag, which makes sense because of the roughly 2.5 meter span, with the main fuselage causing only about 4.5% of the drag, and so on. Our team went through roughly 30+ iterations until we found the stable configuration that we settled on at 0 angle of attack and 0 side slip. And since our last design review, our static margin has moved closer to our 10% target, now sitting at 9.9%. Volume coefficient equations were used to size the horizontal and vertical stabilizers, with our H-stab being slightly undersized to reduce our pitching moment coefficient. And the control surfaces were sized as 25% of mean aerodynamic chord for the ailerons and 30% for the rudder and tail, which were recommended to provide sufficient authority. Our team used AVL to calculate hinge moment coefficients for maximum authority required of the various control surfaces. In order to find the maximum values tested, we were running our UAV's top speed with maximum control surface deflection. Based on the results, the maximum servo torque required was 3.15 kilograms per centimeter, and our team selected a servo from a set of different recommended servos, and ultimately we had them a bit oversized because of its marginal impact on weight while vastly reducing the likelihood of servo failure in flight.
Hello everyone, my name is Yunming. I'm going to present our structural concept and manufacturing plan for our design. As a quick reminder, we are going with a high-wing conventional configuration. Here you can see a little animation and 3-dimensional drawing for our UAS. As for our structural concept, we'll be using different processes to make different parts of the UAS. We'll have a plywood construction of the internal structure where our payload is held. They will be cut by a laser cutter, giving a great precision. We'll use carbon fiber tubes for spars and the tailbone. Then everything will be connected through a 3D printed plate on top of the fuselage. A composite shell will be made by Avid to cover the fuselage and give it protection from belly landing. Here's a more detailed drawing for that plate. 2 carbon fiber sleeves will run through the top of the plate, connecting the wing spars. The boom will come through below, held in place by 4 bolts. And using similar in 3D experience, we conduct the FEA analysis for our wing. 13 newtons of force is applied, resulting in 60 millimeters of deflection, which is well below our maximum allowed displacement. In addition, we also conducted a hand calculation to the boom and yielded a margin of safety of 10. For manufacturing of the UAS, we investigated many processes. We decided to hardwire foam to form the wings and the stabilizers, which will give a smooth surface finish and is relatively easy to use. The fuselage shell again will be made by Avid with layers of bi-directional fiberglass and plain Kevlar. The internal ribs and stringers will be laser cutted. Little cuts will be made on these parts to control the geometry of the structure. The spar and the boom will be purchased from suppliers like Rockquartz Composites. We'll be using carbon fiber through tubes to melt it with the sleeves mentioned earlier. For tooling, we'll be using a combination of hardware machines, since our CNC hardware cannot cut cambered sections, so it will be only used for the stabilizers. The cambered wing will be cut in sections with handheld hardware. For laser cutting, we'll be using plywood sheets ranging from 1/8 of inch to 3 inch, depends on the loading. In addition, we'll be using an assortment of hand tools like drummer to cut the servo placements. Since Georgia Tech is the only school in our team that have hardware machining access, so at the beginning of our manufacturing phase, the wings and stabilizers will be cut at Georgia Tech. Then a single layer of fiberglass will lay out on the foam. The stabilizer will be then shipped to Iowa State for elevator and rudder installation. While the Georgia Tech students will take care of the wings. University of Washington will process the composite fuselage and laser cut the internal components and ship them to Iowa State for sub-assembly and payload integration. Then everything will be shipped back to Georgia Tech for final assembly. The entire process is planned to be completed in 2 months. As required, we constructed a half-scale glider for our UAS. It's constructed mainly with plywood and foam, giving a final weight of 81 ounces. During our flight test, he was able to achieve a glide ratio of 12. And through the construction of the glider, the students at Tech familiarized with the manufacturing method and equipment, gained a better understanding of seizure location, and determined the glide ratios and other parameters. Now I'll hand it over back to Caleb to finish up the presentation.
Hello, everybody again. So for our testing plans, we have done throughout the semester many theoretical analyses using, for instance, for aerodynamics, AVL, XLR5, and VSP. However, we'll need to do real-life tests and theoretical tests as well using CFD and wind tunnel tests at Iowa State, since they have more access to their wind tunnel. We also, as mentioned before, constructed a glider, which gave us an idea about our glide ratio, and from there we were able to get a sense of our L/D. While doing these tests, we'll be looking for some things like incorrect lift and drag calculations, and also we'll be looking at if the airplane stalls at higher speeds than expected. Also, we'll be looking at any disagreement between the simulated and experimental data. For our controls system, there will be tests in this component level and the system level. For the component level, we'll be doing ground tests in the lab, and for the system level, we'll be using a airframe to test our system before we put it on our main aircraft. While doing these tests, we'll be looking for any GPS loss, any improper accelerometer calibration. We'll also look into if our servos are undersized and if there are any incorrect autopilot gains or fail-safe parameters. As for our propulsion tests, we'll be doing a static thrust using a device that you can see in the picture, which we have in Duratech, which will give us a good idea of our thrust in static conditions. And we will compare these data with our model calculations. We'll also do a current draw test to measure how much current is drawn while in different throttle settings to have a better idea about our flight time. We'll also do a temperature test at different throttle settings, but while keeping in mind that the motor can get hot, much hotter at the ground due to the lack of airflow. We will also do a bunch of propeller variations to test for different sizes of the propeller and see which propeller will give us the best performance. While doing these tests, we'll be looking at if our motor is giving us insufficient thrust, or if it exceeds the current draw. Also, if we'll check for if our battery is providing the advertised power storage, and we'll check if any of our components are not matching electrically and if there's any overheating. As for structures, no matter how confident we are with our structure concept, a lot of things can go wrong in that aspect. So we've done FEEA, and we'll be doing more of that. We'll also be doing wing tip tests to measure the wing deflection, different loads, and compare it to our results. We'll be doing a bending and tensile load tests for various components of the system. And last but not least, we'll be doing what we call the Carl Johnson test, where we give our airplane to Mr. Johnson, and he tries to break it as much as he can. And if it survives, it will most certainly survive the air. While we're doing these tests, we'll be looking if we've built a heavier system than expected, and if the system can sustain that. We'll also look into if we have done any incorrect or oversimplified assumptions and calculations. Since the last PDR presentation, our budget has dropped from approximately $4,800 to approximately $4,400. That's due to the fact that we've done more in-depth calculations and removed any redundant components, and more of our payload is going to be simulated. Also, we've found out that we have more components that we needed readily available for free, so that brought our costs down. Looking into next semester, our schedule is going to be our project management team during the break will try to come up with plans for ease of shipping and purchasing. And at the start of the semester, our design team will be working on finalize any minor details with our UAS and UAS model and any documentations for the MRR. As for our manufacturing team, which will be the most extensive portion of our next semester, starting from January 1st to January 14th, we'll be coming up with purchasing lists to have our material and components ready to go when we're ready for manufacturing. From the start of semester to the end of February, we're planning on doing team manufacturing workshops where the team members in various schools can try to get their hand dirty with manufacturing small parts to see how the manufacture process goes and learn from mistakes so that they're more ready for the main manufacturing phase. As throughout the semester, we'll be doing, as from February to April 1st, this is going to be our main manufacturing and testing phase. We would like to finish earlier than that, maybe March 15th, but it's hard given the lack of experience we have. But and also we'll be doing testing and validation throughout the semester. And if everything goes well, we will start our flight tests either between March 15th and April 1st, and our flight demonstration will be late April. And in summary, our major accomplishments this last month, we've developed and tested more of our concepts and designs. We've built a half-scale glider and had a better idea about our design and its performance. We finished our 3DE model, and we increased. And we increased the amount of UAV analysis to justify our design choices. Looking in the next stages, we'll be coming up, like I said before, coming up with our purchasing and list and purchasing these materials, and we'll begin our manufacturing phase. And currently, we're working on our end of semester report. Any questions?
Branko, can you explain a little bit better how is the wing connected to the fuselage? I mean, I see the structure. I see two spars. I see the very efficient 3D printed integrated support. But how is the wing joined with the fuselage? What is the wing structural provisions?
So can you see that purple 3D printed part? So we are also bolt two carbon fiber sleeves onto that part, and that sleeves will connect to the wing spars.
So you're saying those sleeves are integrated with the wing?
Integrated more with the 3D printed part, but and then we'll connect the wing with.
Our line is really breaking. I cannot figure out exactly how the wing attached to the fuselage. You just slide the wings on the side or bolt it on the top? I mean, it's really not clear by looking at this picture.
Basically, the wings are within our wings are going to slide into the carbon fiber tubes that are within the structure on top of the fuselage, and bolts will be inserted for total to keep the wing in place.
Are you saying that the spars are carbon fiber?
Yeah.
Be very careful with the transition between the wing and the fuselage. The carbon fiber doesn't like concentrated loads and out of plane load introduction. So make sure you have some transition sleeve where the parting line between the wing and the fuselage is.
Thank you.
Yeah. Thank you.
Also, it's not quite clear to me where your engine is, engine mount. Where's that load path? How's that structure look like? How's that load distribution where your engine housing is introduced to the fuselage? Doesn't look, I understand this is just conceptual, but I am not understanding where's the load path there.
So there will be a carbon fiber disc that will drill 4 holes into to connect to the motor, and that disc will be secured to the fuselage, which is the load carrying component.
You may need some additional internal structure inside the fuselage to distribute that load into the fuselage monocoque.
Yes, the internal structure comes around the motor, which is at the very front. It comes around the backside, and it also goes around the circumference of the motor.
Okay.
Thank you for that. And is there any other questions?
I'll pitch you guys one if nobody else is going to chime in. Since you guys are not going to purchase the expensive sensors that your system would be using to give you some kind of data on your flight or your mission success, I suppose, are you planning on doing anything to simulate maybe a found hiker and seeing if your system works as is? As it is right now, since you're not going to be flying with the sniffer or the personal locator beacon or whatever the other payload component was, what are you going to do to prove that you can complete your mission?
We're gonna simulate our mission, and we're also, in terms of weights, we're gonna simulate the weights of the components. So in terms of flight stability and everything, we're covering that. As for actual system integration and data collection. We'll be doing more research and making sure our components are able to communicate with each other. I mean, we've done the research already for that, and we'll be doing more of that as we go. But like you said, we're not actually actually buying these products, so we haven't put much effort into actually simulating as of right now. But this is something we can go do if need be.
I think you mostly answered it, but I mean, you understand what I'm saying, right? You're saying that the UAV shall continually communicate UAV position to the ground station. That's fine. You're hoping to transmit data to the ground station, right, about the location of a hiker?
Correct. Yes.
Okay. I think you just need to have a plan to actually be able to do that. Yeah, even if it's pumping in an artificial position somehow, like with your Raspberry Pi, that would be the quick and easy way, I think, and make sure that you can actually get the results that you're looking for. That's all I have for you. We still have a couple minutes. If any other Boeing and/or student teams or faculty members have any questions. If not, we can get Team 6